So I want to take a moment to go through the day 10 part 1 solution. This isn't going to include part 2 because I haven't been able to get that to complete yet. I believe it's correct, but I haven't gotten it to complete. So day 10 is actually a pathfinding problem, at least part 1. Part 2 is, I believe, also a pathfinding problem, but there's some sort of optimization that I haven't quite figured out. So let's look at two things. One, I'm going to briefly show the pathfinding part, but the cool part is parsing data. So let's look at part 1. So part 1 here. Um, I'm using pariter. This is from the Rayon system. We don't have to do it for part 1, but pariter is going to run every shortest path in parallel and then sum them once they're done. So the shortest path in pathlights looks like this. So we have our machine state. This is our desired state of the lights that we want to be turned on. And the actions are button press action, which is a vector of sort of toggles. Um, and this is just it. um, we create a machine starting state that has unlit lights. So this is our starting state. And using Dijkstra's algorithm, if you look at their input, we have a starting state, the successors. So at every iteration, given a state, where can we go to next? And then some sort of success criteria. And that's it. So we pass in our starting state. We have our what we're going to do on every step. So this is the successors of some given state. And then we check to see if this is the desired state, and then we're going to return basically the total cost. So if we look at our successors is just this. We're going to take our actions and we're going to apply the action to there, and we're going to return that. And this expects to get a tuple of the current machine state and the cost of going from one state to another. And that's like literally it. It's a pathfinding problem. Once you know how to map your problem into something that's going to fit into this, it's very trivial to run. So similarly, the shortest path for joltages looks almost identical. We have joltages successors, which right now I'm doing two things. I'm checking to see if there's like an overvoltage. So like if continuing to push it's always going to be overvoltage, we're not going to do anything with it. Otherwise, we effectively do the same thing. We apply the action to every joltage that's in there. But this takes too long. It does finish for some of them. So when I run pariter on this, I do get some that do finish, but the very first one doesn't. So they're just, I guess, too many states to go into, and it never finishes for this one. It finishes some of these other smaller ones, probably trying to scan it. This one only has 4, so it probably finishes this one quickly. But for ones that have a lot of possible states, it doesn't seem to finish. So we got to find a better solution for that. Let me look at the parsing. Parsing is really cool. So parsing, let's look at our sample here. So one thing you can do is you can split this by space, and the first one's going to be this, the last one's going to be this, and everything else in between is going to be these. So you can certainly do splits and maps over those splits to get what you're looking for. However, I wanted to use um, the Nom Parsing library. So Nom is awesome. It takes a little while to understand Nom. It's kind of like regular expressions. Like once you get it, you're like, oh yeah, I can build that up here. So let's look at what parse data looks like. Um, this is basically mapping over lines, and we end up calling this parse machine description. So parse machine description is this. We take our input, our line that represents our machine, and iResult is a nom type. It's it's a way to combine um, what we want to return and a the what we didn't parse, as well as errors that we might have encountered. So anything that could fail is going to go up through this iResult type. And this is what our parser looks like. It basically says, okay, we have our lights. We're going to parse the lights. We're going to parse the space. So you have to think of this like sequentially going through this. We're going to parse the lights. We're going to parse the space. We're going to parse many button presses in another space. And then we're going to parse the voltage requirements. Like that describes it. So let's drill down. So parsing the light description. So our light description looks like this, where we start with a bracket. We have either a period or a pound sign, and that continues until we get another bracket. So Nom has this parser called delimited, and it's heavily based on generics, but it says, okay, what's the first thing we're going to parse? What's the second thing we're going to parse? And what's the third thing we're going to parse? It throws out the first and third and only returns the middle part here. So that's what we have. We're going to parse a left bracket. We're going to parse many, 0 or more, um, of these things, a button parser, and then we're going to parse that. So button parser just um, it looks for one of these two things, and then we call light from care. So for any one of these, we call light from care. MapRes is going to be able to properly propagate result types up, wrapping it into iResults, and um, we just pass in the input. So we get one of those, we just turn that into a character. So our whole parser here is like 70 lines. And I get that the other version of it, if we did a big split and joins and stuff like that, it would be shorter, perhaps, but this is a way of creating a much more powerful parsing system that can parse probably literally anything you want in a description that's like, to parse this thing, this is what it looks like. It's just it's phenomenal how well this works, how terse it is. So certainly worth looking at it. Look at the knob crate. Definitely a something to have in your arsenal where you need to parse custom data types.